Hello, I'm JW. This time looking at circuit breakers and what the different letters on the front actually mean, and these are typically B, C and D. And you've probably seen these on the front of circuit breakers, and you get things such as B32, which will be a type B, 32 amps, or say something like C6, which will be a type C, 6 amps. So we're going to have a look at what those letters actually mean, and different circumstances where you may need to use those. And also the fact that you can't just go swapping them around without actually checking the circuit first, because in some cases it's not actually possible to fit certain types of circuit breakers to certain circuits, and if you do, then the result is going to be overheating, fire, and who knows what else. Now, on a typical circuit breaker, the rating is shown on the front. I've got here, this is a 32 amp one, and it says here B32, so it's a type B, and it's 32 amps. And of course you can get various different values, and obviously the different types as well. And the same applies to RCBOs, which are the circuit breaker and RCD combined. And here's another one. This is also B32. So again, just printed on the front there. This also has the additional information for the RCD part. So regardless of whether it's an actual circuit breaker or RCBO, it's all just printed on the front there. And generally just a question of reading what's on the front of the device. Now, I've seen circuit breakers in previous videos, including what's actually inside them, and circuit breakers contain two separate elements inside, and these are thermal and magnetic. And the thermal part is usually a strip, or bimetallic strip, and that only reacts to moderate sort of overloads, and basically that's the strip which then will slowly bend as it heats up. Once it gets to a certain temperature, it will then trip the circuit breaker. So those are really just for overloads, and as example, that might be the sort of thing if you say had a 6 amp circuit breaker, and if you say connected to a 10 amp load to that. And that part of it is actually quite slow because it has to rely on the thing actually heating up, so that typically is going to take seconds, or in some cases even minutes, before the thing actually trips. But again, it's only for sort of moderate overloads, so it does have current just flowing there, but it's just more than the rating of the device. Now, the magnetic part is for short circuits, and this is the kind of thing where you have a fault, say between line and earth, or between line and neutral, and the result in this case is that the current will flow is going to be significantly higher than you're going to get into some sort of overload situation. Typically it could be in the order of hundreds of amps, or in some cases many thousands of amps. Because basically you're putting a wire directly between two of these things, and the current is going to be limited by the impedance of the circuit, which in most cases is going to be very small, in the order of only a few ohms or even less than 1 ohm. And this part is designed to react very quickly, not quite instantly, but pretty much as near as you can get. Now, for the types of circuit breakers you can get, which are the say B, C and D being the most common, this only applies to the magnetic part. The thermal part is actually the same regardless of the type that you've got. So we're only talking about the magnetic part here. The thermal overload part in there is going to be the same, say, in any particular type you have got. And the most common types available are B, C and D. Now, there are a couple of others which are K and Z, but those are fairly uncommon, and certainly B, C and D are the ones you're going to find in most applications. Now, before B, C and D came along, there was another system of defining what types these were, and that system actually was a number system. It was 1, 2, 3 or 4. Now, this hasn't been used for quite a number of years, but of course there's still lots of circuit breakers out there installed which will have this on the front, and these typically on the front will say things like type 1, type 2 or whatever, rather than just having the letter in front of the rating. So not something you're going to actually be installing, but you will find them, say, in older installations. They're still relatively common, and you can still keep using these. There's no reason not to. It's just that this is a different rating system to the letters we've got over there. Now, I'll have a look at the three most common types, which are B, C and D. I'll have a look at the other ones a bit later on. Now, the letters indicate the trip current that the particular circuit breaker will trip at. And in terms of a short circuit, say for example a 6 amp circuit breaker does not trip when the current actually exceeds 6 amps. And for the type B, which say is probably the more common version there, the actual tripping point is between 3 times and 5 times the rated current. So for a 6 amp circuit breaker, then that would be 3 times 6 would be 18 amps, and at the upper end of the scale that would be 5 times 6, which of course would be 30. So to trip a 6 amp circuit breaker nearly instantaneously, then you would need to apply current of somewhere between 18 and 30 amps to it, not anywhere near the 6. And this may seem surprising, but of course this is actually an intentional design. If you had a circuit breaker which, say, tripped at sort of 6.1 amps instantly, it would actually be completely useless to use, because when you turn on pretty much any piece of electrical equipment, there's usually a bit of a surge initially, and if, say, this was, say, an incandescent lamp or something, that's because the filament has a lower resistance when it's cold, so you get that sort of initial burst of electricity going through there, where the current is much higher. The same thing also applies to motors and things like that, because of course it's a magnetic device, and it's time between it power being applied and the magnetic field establishing, you can get a fairly high current there. And even things with like power supplies for computers and whatever else, when you switch it on, the capacitors inside have to actually charge up, and before they're charged they're presenting what's almost a short circuit to the actual supply, so again you get a bit of a surge when you turn those on. So if it did trip at, say, 6.01 amps or something, all that would happen is every time you turn anything on in your house or wherever, the circuits would just trip out all the time and be useless. So this is actually a design feature. So in the case of the Type B, somewhere between 3 and 5 times the rated current. Now the Type C, which is used generally for things which have a larger switch-on surge, this actually will trip somewhere between 5 times and 10 times the rated current. So in the case of, say, a 6 amp circuit breaker, then the tripping point would be somewhere between 30 amps, which would be the 5 times 6, or 60 amps, which of course is 10 times 6. And for the Type D, again, similar kind of procedure here, although the difference here is that it's actually somewhere between 10 times and 20 times. So again, if it was a 6 amp circuit breaker or a D6, the tripping current for that would be somewhere in the region of 60 amps if it was the 10 times to 120 amps if it was the 20 times. These are given as a range because it's not possible to make a magnetic device with a mechanical piece inside which will trip exactly at a particular current, so there's always a range of currents that it will trip at, but it will be somewhere within those parameters. Now the main reason to having these different ratings is that most pieces of equipment will have various types of switch-on surges or starting currents. So for normal applications, say in your house or whatever, Type B would be the most common because most of the stuff in your house doesn't have a particularly large surge when you switch it on. Say things like incandescent lamps or whatever do have a bit there, but so they're pretty much gone anyway, and certainly other equipment not normally going to be much of a problem. But it may be necessary to use, say, Type Cs and even Type D in some cases, because certain types of equipment do have a much larger surge when you turn them on. Things like electric motors would be a fairly common example of that, and it's often the case you may need to use Type Cs for electric motors, simply because when you turn on a motor, the initial current to start it is significantly greater than the current it would run at. And in some cases you may need to use Type C on certain types of lighting, because I would say with magnetic ballasts and things inside, again it's the same sort of situation. Quite a large current when you switch the thing on. And Type D is just an extension of that, so again fairly less likely, but there are certain types of equipment where you would need to have a Type D, because when you turn the thing on, the initial current is very large compared to the running current, so it may be many times greater, and again the Type D may be required there. Now we'll often see Type C sold as motor rated, but that's not really true at all. It just happens that the current they trip at is larger than the Type B. They may well be used for motors quite often, but they can be used for plenty of other stuff as well. And in some cases it may not be appropriate to use a Type C for a motor, you may need a Type D instead, or in other cases a Type B may do just fine. So just because they're sold as a motor rated or whatever, it does not mean that, oh, you've got a motor, shove a Type C on it automatically. Same as it doesn't mean, oh, we've got a welder, bung a Type D on, because again there are other things to consider. Now the older type of classification for circuit breakers was a numeric system, and that was basically types 1, 2, 3 and 4, and so they don't make those anymore, but there's still plenty of them out there. It's quite common to see those, certainly in older installations, and it's a very similar arrangement, although the actual ratings are slightly different. And the Type 1 is going to trip somewhere between 2.7 times and 4 times the current, So that's roughly equivalent to a type B, although the actual numbers are slightly lower because that was obviously 3 to 5 there. So quite common to see those in many sort of domestic type properties. The type 2 is somewhere between 4 times and 7 times, and you might say that's sort of in the general area of a type C, although again the numbers are slightly lower. The type 3 was 7 times to 10 times, so again that's still in the range of the current type C one. And the type 4 is somewhere between 10 times and unfortunately 50 times the rated current. Now type 4s are fairly uncommon, and if you do actually find those, it's well worth getting the actual specifications for that particular one from the manufacturer or whoever actually made the thing, because they don't all go up to 50 times. Some of them actually are quite a lot lower than that. And again, some of these other ratings here may be slightly different for different manufacturers. The problem with the type 4, if it does go up to 50 times, and you had, say, a moderately rated item, then the current to trip it could actually be so massive that you would never be able to get that from the supply, in which case if a fault occurred it wouldn't actually disconnect. So in theory they're up to 50 times, but in reality well worth getting the specifications for that particular one, because say the manufacturer may have made it to a slightly different range, so well worth getting that to check. Type 4s are fairly uncommon, not likely to be seeing many of those around, but type 1 and 2 is fairly common, and even type 3s do still show up. Now, if you do forget what these are, because let's face it, you're not going to necessarily remember all of this, then the information can be found. It's not actually in the wiring regulations for these ones. It can be found in the on-site guide. This is the current edition here, the yellow one. And we can see inside here there's a table here in the section 7, which just gives you the various types there and the actual trip current that you've got. So it's in there in the smaller actual guide there, not in the main regulations. Although, of course, the B, C and D types obviously are, because those are the current ones. Now, in terms of fitting the particular circuit breaker, before you've chosen the type B, C and D, you need to make sure that it's actually appropriate and safe to actually install one of these things. So what you can't do is just say, well, we've got a type C installed here, but the thing we're turning on is still tripping, so let's just shove in a type D instead. And the reason for this is because the impedance of the circuit needs to be low enough to ensure that the thing will actually disconnect when a fault occurs, because bearing in mind, certainly on a type D, you could be looking up to 20 times the rating of the circuit breaker to actually trip the thing. And of course, if you've got a fairly high impedance circuit, even shorting out between the two conductors may not actually produce a current of that required amount. So before changing the circuit breaker type, or in fact installing the first one in the first place, you do need to check the impedance of the circuit and confirm that it is actually within the requirements for the particular thing that you're using. And there's a table here, in fact there's several of them for different purposes in the regulations. Again, this is the yellow edition here, and this gives you some examples of the maximum earth fault loop impedance for various types of circuit breakers. So you can see along the top here, got various ratings, starting from 3 going up to 125. And if you have a look at that 6 amp one, so similar to what we were just using there, and then this here giving the total impedance, or ZS, so that's the external impedance and the impedance of the circuit itself. And these are actually the maximum values you can have. So at the top here we've got type B, which is say the most common. So for a 6 amp circuit breaker, the maximum impedance is 7.26 ohms. So that's actually pretty easy to get to. Not really going to be a problem. But if you wanted to change to, say, a type C, then the maximum impedance is only 3.64. And you'll notice that 3.64 is actually half of 7.28. And of course the reason for this is this thing will trip up to a current of 5 times. This thing will trip up to a current of 10 times. So you need twice as much current to trip the type C. Therefore you need half the impedance to get the same amount of current. And conversely, if you move up to the type D, again the 6 amp one here, and we'll find that the impedance is actually even lower. And again, it's half again, because again you're going from a 10 times current here to the type D, which was seen previously requires 20 times. So if you measure the impedance of a particular lighting circuit, for example, and found it was, say, something like 4 ohms, fairly long one, then of course fitting a type B is perfectly acceptable. But fitting a type C would not be, because the 4 ohms is greater than we've got here, so that if a fault occurs, the current that flows is not going to be sufficient to disconnect the thing within the required time. Time in this case is the 0.4 seconds, which is applicable to most circuits. And again, if you had to say an impedance of 4 ohms there, you most definitely couldn't fit a Type D either, because the impedance is required is a maximum of 1.8. And again, in that case, it wouldn't actually trip within the required time. And in very extreme cases, you may find it doesn't actually trip at all. All that would happen is that the cables would just get rather hot and melt, possibly set on fire. The circuit breaker would just sit there doing very little. So it is important to check these things before just shoving in the circuit breaker. Now, of course, on a 6 amp circuit, it's fairly unlikely you're going to have impedances anywhere near these things, unless it's, say, ridiculously long or something. But say have a look at the column here for 32 amp circuit breakers. Even on a Type B, the maximum impedance is only 1.37 ohms. And then, of course, once you get into Type C, you're needing a maximum impedance of 0.68. And bearing in mind, if you've got a certain type of supply, the external impedance could be a large proportion of this. So either you're going to have a very short circuit, as in not very long, or you're not going to be able to fit a Type C. And of course, once you move into the Type D, it's even worse. So for a 32 amp Type D, maximum impedance of 0.34 ohms, so that's the circuit and whatever's outside. So it can actually be quite difficult to meet these things. So in many cases, it's not actually possible to fit a Type D at all. Now this table also has a additional line here, which is also for the Type D, which is for a 5-second disconnection time. In these cases, you can have a somewhat higher impedance there, but 5-second disconnection is not applicable to quite a lot of circuits, though in some cases that can be used. But we'll have a look at the disconnection times at a later date. But certainly for most standard circuits, your 0.4 seconds is the required time for disconnection, and then of course these values here will apply. And certainly if you consider if you had a TNS type of supply in the UK, the external impedance of those can be anything up to 0.8 ohms. And then of course you have to add on the impedance of the circuit, but even if you had your 0.8 ohms, so you had a 40 amp Type C, your minimum impedance required is actually 0.55. So if you've got a TNS supply and you happen to measure the external impedance to say 0.7, then it's pretty much game over for the Type C, because the maximum is 0.55. And if you've already got, say, 0.6 or 0.7 at the origin, then pretty obviously fitting a Type C is not going to happen. And of course with the D it's even worse. And certainly if you get them to, say, the high rating of, say, 63 amps and above, the actual impedance you need for the whole system is incredibly low. Not something you're going to find on the majority of installations. Now there are a couple of other types which, although are available, they're fairly uncommon, but nevertheless they do exist. So the first one of which is the Type K, and Type K will trip somewhere between 10 times and 14 times. So in that regard it's similar to the Type D, the only difference being is that it's between 10 to 14, whereas the D was of course 10 to 20. So similar usage for the Type D. The difference is its upper level is considerably lower, so that may be useful in some applications. And then the other one, which again is a fairly uncommon type, is the Type Z, and this actually trips between 2 times and 3 times the current. And again, this is actually below the rating of the Type B, as we saw the B before was 3 to 5. So this would be the kind of thing you would use on a circuit that either had a very high impedance, and therefore you only need a very small current to trip the thing. Typically used on things like control circuits and that sort of thing, but not a particularly common item, but nevertheless these things do exist and do have usage in certain applications. And the final point, there is no Type A, despite that might seem being fairly obvious. The reason being is, of course, that if you put A on a device, then it's probably going to mean amps. So clearly that would be leading to a bit of confusion, hence why the numbering starts at B rather than A. So if you see A on a device, it does actually just mean amps as that one, but hence you're not going to see it on a circuit breaker marking the type. So no Type A, but say B, C and D are available, and of course K and Z are also available as well. Now in terms of where these things fit in on an actual graph, I've got a diagram here which kind of shows the tripping current for the full set of the 5 types of circuit breaker. And you can get these for any type of circuit breaker, typically from the manufacturers, and they're all going to be fairly similar, although say in some cases there may be some minor differences, particularly with the older Type 4s, for example. And essentially what we've got here is along the bottom of the graph here we've got the multiple of the rated current. So that's the values we were just talking about there. So we've got type B in the middle there. You see it starts between 3 times and 5 times, and then the type C is between 5 and 10, and type D is between 10 and 20. And this particular one also has the type Z and K, so that's the 2 to 3 there at the bottom, sort of below the B there, and then K is sort of fitting in as sort of a subset of D there between 10 and 14. So for any particular rating of circuit breaker, then along the bottom here is the multiple of it. So if I had a 6 amp circuit breaker, you can see there that the type C would be tripping somewhere between 5 times, which would be 30 amps, and 10 times, which would be 60. So pretty much what we saw previously. Now on the left of the graph there, you can see the actual time in seconds or minutes right at the top there. And that's actually how long it would take to trip for any particular current. So you can see that the first part of the graph, starting by about 0.02 seconds and going upwards, is virtually sort of vertical. So essentially in those cases it's going to trip nearly instantaneously, sort of 0.02 seconds or whatever. And of course that's the whole intent of these devices, that once you get to the specific current you've got, then it will actually trip. And the difference between the two lines, so say on the B between 3 and 5, is just that it will trip somewhere between the current there. The actual time it takes to trip is going to be the same, it just depends on the individual device. Now the top part of this graph, which is the curved section, that's actually the thermal part of the circuit breaker, and that's actually the same for all of the types, hence the lettering doesn't actually extend up that far. And you can see there that if you say applied a current of say 1.5 times, follow the line up there, then it actually basically hits the time at around 20 seconds. Because again, the thermal part is very slow, it takes time to heat up. And of course that's designed for moderate overloads like that. So that does take quite a long time, and again, as we saw before, that is actually the same for all types of circuit breaker. But for the magnetic part, which is essentially the vertical section, it's sort of near instantaneous provided you're within the particular ratings you've got, so say 3 to 5 for the type B and so on. And that little piece at the bottom where the line sort of starts to curve away in the other direction, that's actually where the mechanical parts of the circuit breaker actually come into operation, because no matter how much current you're going to apply, there's always going to be a certain amount of time for the mechanical contacts to open, hence it starts to curve away in the other direction as you get right down to the tiny times at the bottom. But suffice to say, they're all going to trip in that sort of range in the middle. It just depends on what the actual type is as to where the current required is. So look there at circuit breakers and the different types, and it's important to realise you can't just go shoving a type C or D inside there just because the thing you have just happens to trip when you switch it on. You do need to actually check the circuit first and ensure that the impedance is actually low enough so you can fit that type C or D. Otherwise, if you're going to fit one of those in there and it's not low enough, then the thing is not going to trip in the required time, and in extreme circumstances, of course, may not trip at all. Certainly if you shoved a high rating type D in somewhere, and of course it may just never trip at all if a fault occurred, and the result of that would be cables melting, overheating, and who knows what else. So definitely need to check the circuit first. And also bear in mind there may be circumstances where it's simply not possible to fit a certain type of circuit breaker. So if you say had an external impedance on the supply of say 0.5 ohms, there's simply no way you're going to be able to fit a high rated type D in there, because even if you put the thing at the origin and didn't have any circuit at all, the 0.5 ohms could actually still be far too high to allow the type D to disconnect. So if you had say a 40 amp or something in that area. And don't also be fooled into thinking you can just shove an RCD on there, because although an RCD will trip when a fault between line and earth occurs, of course it does not work when there's a fault between line and neutral. So unless you've got a very low impedance on there, again the same problem could occur, because if you've got a moderately large impedance between line and neutral and say a large rating type D, no RC is going to help you there. And again the end result is that it's not going to trip in the correct time or at all, resulting in cables being damaged. So that's all for this time. And I've put some links here in the description to that file there, and also to the videos on circuit breakers in the past. So until next time, thanks for watching.